Hi, I'm Mila, and today I'll be explaining the concept of time dilation. Hi, I'm Mila, and today I'll be explaining the concept of time dilation. So first let's start off with what is time dilation? Well, time dilation is the slowing down of time in one frame of reference that is moving relative to someone that is observing that frame from another frame of reference. Now that's a bit wordy and can be a bit confusing, which is why we're going through it today. We'll first start off with Einstein. He was the first to recognize this odd behavior of time in different frames of reference, and this was through his two postulates. The first being that the laws of physics remain the same in all inertial frames of reference, so there's no experiment that you could conduct to tell you whether you are moving at a constant speed or just not moving. And the second postulate being that the speed of light is independent from the motion of its source and its observer from any inertial frames of reference. So if I'm looking at my lamp over there, speed of light is still going to be the speed of light. It's still going to be 3 times 10 to the 8 meters per second. So after considering both of these postulates and realizing that does something weird, Einstein then conducted a thought experiment to further understand this weird characteristic of time. Now, a thought experiment isn't anything too exciting. You can grab a piece of paper or you can just do it in your head and watch me do it on my whiteboard. We're just going to conceptualize an experiment or a situation and try and figure out what this tells us about physics. So let's take, for example, a light clock that includes a set of mirrors, one at the top and one at the bottom. And this light clock sends a pulse of light up and a pulse of light down in 1 second, at the speed of light, of course. Now let's say that this clock is actually moving in a minecart at a constant speed horizontally. If we were an observer or person just in this cart, let's say we're right here, and we're looking at this light, what kind of motion would we see that light do? So we're observer 1 and we're in this cart. From our clock, the light just goes up and down. So all we're going to see is the light going up and the light going back down. That's all there is. We're moving, we're within this minecart, we're watching the light go up and down. Now let's say our friend Henry is standing out here and he's watching this minecart with us and our light clock go by. What is he going to see as the light clock passes by? What kind of motion of light will he observe? Well, if you have something that is going up and down, if we have something that is going up and down in one direction, and then starts moving in the other direction, what kind of motion is it going to make? Well, let's see. At the start, I was just moving my hand up and down, then I started moving to the left. To the left. So what we've created are diagonals. Diagonals that actually form a triangle with a horizontal. And we can notice, and we know from our trigonometry lessons in math class and all the geometry that we've done, that these diagonals are actually longer than these short bursts of light going up and down. So for observer 2, the light has traveled a farther distance. And in order to do that, since we know from V equals d over t, it must have traveled a longer time because the speed of light needs to stay the same. If we increase the distance, we also need to increase the time accordingly so that the velocity will stay at the speed of light at 3 times 10 to the 8. So what this tells us is that for observer 2, time slowed down. For observer 1, for us, time stayed the same. What we call these two times, for observer 1, that is proper time. It is the time measured in the inertial frame. For observer 2, we call this time measured time. And this is the time that we measured outside of the inertial frame, the non-inertial frame. And it is important to note that the measured time was larger than the proper time, and this will always be the case so long as the velocity is greater than 0. Now these two times are what we call relativistic time, which is time that is not absolute or set, but it changes relative to the observer. As we can see, for observer 2, the time took longer. For observer 1, time was shorter. And I have two easy ways. I've already sort of mentioned them, but I'll make it a bit more clear to remember what measured time is in an equation or in a question, and what proper time is. So my first way is this. The proper time is measured in an inertial frame of reference. Let's say you're in a spaceship and you're looking at a clock. That's going to be your proper time. Or you're inside of a car and you throw a ball up. That's going to be your inertial frame. However, measured time is within a non-inertial frame, so you're watching something accelerate past you. And then the second way, which is much easier to remember, it's my favorite, and I've already sort of mentioned it, is that your measured time will always be larger than your proper time. So if you're doing an equation, a math equation regarding time dilation, remember that your measured time is always larger than your proper time. So if you get something else, you've messed up. Now, from all of this, from Einstein's thought experiment, what we get is actually an equation regarding both proper time and measured time. And this equation is very important because we use it in a lot of science, especially in engineering and GPS, which I've actually written a little paragraph underneath this video about, and how time dilation affects GPS, or global positioning satellites. So this equation that we use is this. The time measured, also known as Tm, the measured time, is equal to the proper time, which we refer to as Ts, over the square root of 1 minus our velocity, or speed squared, over the speed of light squared. So Ts is our proper time. I understand that it's a weird variable, but we simply couldn't have a variable called Tp, because that's toilet paper. And then we have our velocity down here. And always remember, when you're doing this equation, to square the velocity. I, many of a time, have messed up and forgotten to square the velocity and have sat there wondering, why isn't my answer correct? So always remember these two squares. And then our variable c is just the speed of light. Now I'll lift my computer up so that you can see a better perspective of this equation, and I'll also put a link below this video to how we actually got this equation, so the derivation of this equation, and just a different picture of this equation so you can see it a bit better. In that derivation document as well, they use u instead of v for velocity. It's just their variable choice. It's nothing big. So this is all theoretical, so it's all nice and fun, right? Well, it's actually experimental as well. There were many experiments conducted in the 60s and 70s and so on to prove Einstein's theory of time dilation. I've included a link to one of these documentaries of an experiment from the 60s by Professor Frisch from MIT and Professor Smith from the University of Illinois, and how they proved this equation as well as Einstein's theory of time dilation and special relativity. And they used a particle called a mu meson, which is a subatomic particle, sort of like an electron, and they measured the elapsed time when sending a beam of particles back and forth. So this documentary is from the 60s, but it's very nice and it's very educational if you want to get a better look at time dilation and actual experiments. So that's pretty much it. To summarize, we have measured time, which is longer, and what you're looking at from a non-inertial frame of reference. So when you see something accelerate, those are your diagonals. And then you have proper time, which is just what you're looking at inside of an inertial frame of reference. You're just watching light go up and down. You're watching something stay constant. And then remember, that's your equation. Remember to square things. and have fun with time dilation in physics. Bye, guys.